Hi, everybody, thanks for coming back. Right, so I want to remind you of what we did last hour. This is a picture of the simplicial closure of outer space. And the red stuff is the stuff that's not in outer space, but it's in infinity. And so I call that CD infinity. It's the simplicial closure minus the interior clouds. And what I want to do now is where am I? Yeah. Talk about really these graph complexes that we described in the first part of the hour to these spaces. So let's start with the even commutative graph complex, GC2. So notice that the vertices of one of the simplices associated to a marked graph correspond to the edges of the graph. So when you orient the simplex, what you do, you order its vertices. So an orientation of the simplex corresponds to an ordering of the edges of the graph. So now let's look at the quotient space, the simplicial closure, modulo out of Fn. That's calling that delta n star, and calling that delta n star. And then delta n infinity is supposed to be the quotient of the part of infinity modulo out of Fn. So, right. If you just look at delta n, right, forget delta n star at the moment, just look at the interior simplices. This quotient has one cell, which is the quotient of the simplex modulo the action of the automorphism group of the graph. The automorphism group of the graph is like the isometries of the graph. And so, yeah. So for instance, if your graph was this, and you look at the isometries, the automorphisms of the graph is there's a permutation of the edges, and there's a flip, and the quotient of this whole by this group of automorphisms is just one piece of the 1/6 of the simplex. Okay, so here's a fact about if you have a quotient of a sphere by a finite group, it's either a rational homology sphere or a disk. So this cell C of G, well, that's the cone on the sphere, on the boundary sphere. And the quotient by I of G, well, that's either a homology sphere or a disk. So the quotient cell is a cone on a rational homology sphere or a disk. So when you get a rational homology sphere and when you get a disk, if the group of automorphisms has an odd element, then so that's an odd permutation of the vertices of the edges, then it's a cone on a disk. And if it's doesn't have any such odd automorphism, then it's a cone on the sphere. So let's think about the chain complex for this quotient space. You can think of it as having one generator for every graph, which doesn't have any odd automorphisms. That's supposed to be getting sounding familiar. And the orientation on the quotient sphere is induced by the orientation on the original sphere. So so you get an orientation on these quotient cells. They're not cells, they're cones on homology spheres, or cones on homology disks. But as far as homology is concerned, there are cones on spheres or cones on disks. Cones on disks, you don't need them. If you're trying to compute the homology of some space, and one of your cells is a cone on a disk, you can just forget it. You don't need it. So the upshot of all of this little discussion about homology spheres and homology disks is that the chain complex, the relativity chain complex, I keep forgetting this. So the relative chain complex only has cells, all the cells at infinity are zero, since we're doing the relative chains. So we're only interested in the cells in the interior, and that's got one generator for each graph with no odd automorphisms. Okay, so if you follow that logic from the beginning to the end, right. We have this space over here, and the space is at infinity. And we're looking at the relative chains. And we get one generator for each graph with no automorphisms. And if you check the boundary operators, is exactly the boundary. So that's just exactly the graphs we're using to define GC2, at least in rank n. So we've got a vector space that has one generator for each graph, for each even graph. And yeah, so and the boundary, you can check that the boundary map is what it ought to be. The boundary map in this simplified quotient is the same as the boundary map in the Kontsevich's commutative graph complex. So that gives us a topological interpretation of GC2. It's just the chain complex of, I don't know why I did this, the relative space, the implicit closure modulo delta n. So this makes the topologist happen. Instead of an abstract complex of vector spaces, we have something that actually is the chain complex for a relative chain complex anyway for the topological space. Okay, so that was easy. So now let's move on to the Lie graph complex, and I'll do the odd Lie graph complex because that's what I've talked about so far. So to think about this, I'm going to pass to the spine. Let me see. Yeah. So let me remind you of a picture of the spine in rank 2, at least looking from above. The spine has a vertex in the middle of each simplex that's in outer space, and an edge between two vertices, if you can get, so this vertex corresponds to that graph, and this vertex corresponds to that graph. And the way you get from the theta graph to the rows is you collapse the middle edge, which is indicated by this picture. You take your theta graph and collapse the middle edge. So you can think of that graph with a forest mark as a descriptor of that cube, that one-dimensional cube. Why do they call it a cube? It's also one simplex. It turns out that the spine has the structure of a cube complex for every n. And what are the cubes? The cubes are given by pairs consisting of a graph, a forest in the graph, and of course the marking. I haven't drawn the marking in this picture, but how do I see a cube of graphs? Well, this particular cube, for instance, is associated to the middle graph with those two forests. At one corner of the cube, I have the same graph, but no forest edges. And at the opposite corner of the cube, I have the graph where those forest edges have been collapsed. And how do I get from the top right corner to the bottom left corner? I collapse the bottom edge, and I collapsed the middle edge over there. But I could have got the same place by collapsing the left-hand edge first, and then collapsing the right-hand edge. So in other words, ordering the edges of this forest tells me, how to orient that cube. So if I collapse the bottom edge first, I go over the top, and then collapse the second edge, I go down. So that gives me orientation like that. So in other words, I have Kn is a bunch of cubes. The cubes are all oriented. And how do I get the orientation? I orient them by ordering the edges of the forest. This is supposed to make you remember what I talked about an hour ago about the Lie graph complex. Let me remind you about that. What's an odd-oriented Lie graph? Well, this is a complicated thing, but it's equivalent to a pair consisting of a graph and a forest. The graph was supposed to be trivalent. That's a little different. But it was oriented the same way. It was oriented by ordering the edges of F. And if I had an odd orientation, it was supposed to be 0. And then there were these IHX relations. So this almost looks like the chain complex, the cellular chain complex for the quotient space of the spine out of the fin. We have the same story about what are the generators of the quotient space. You've got a cell, which is a cone on homology sphere or a disk. If you've got an odd automorphism, the cell is a cone on homology disk, and you can ignore it. Otherwise, it's a cone on rational homology sphere. That's exactly the same story we have for the commutative graph complex. But what's different here from the picture I just showed you is my graphs are all supposed to be trivalent. So the proposition, or the theorem, is that actually the graph complex is quasi-isomorphic to the chains, the cochains on this quotient complex. So it's not exactly the same complex, it's not exactly the same chains, but it's quasi-isomorphic. In other words, it has the same homology. And the proof is easy. So you have K chains. Remember, K chains were graphs with K vertices. You can also count the number of trees in the forest, and that gives you a double decomposition of the chain complex for this. So this is trivalent graphs with a maximum tree. And then, right, these are all let's see which one I'm doing. This is still trivalent graphs. And I removed an edge from the maximal tree, so I get 2 trees. Here's how I remove 2 edges, so I get trivalent, 3 trees. And going down, I'm collapsing edges, so I get one 4-valent vertex and a maximum tree, and etc. Okay, so as I go down in these columns, I get graphs with fewer and fewer vertices. The CK is how does it go? Yeah. So the K-dimensional, yeah, the K cubes correspond to graphs with K tree with forests with K edges. So that's CK minus 1, CK minus, yeah. This is the chain complex for my whole space up there is those are, yeah. That's what it looks like. The diagonal things give me the K cells, the K cubes. And notice I've drawn a co-boundary operator instead of an operator. a boundary operator. There's a reason for that. So what does the boundary operator do? It takes an edge and collapses it. So what does a co-boundary do? It should take a vertex and expand it into two vertices. So let me, so if I have a graph and it was trivalent and I collapsed it to get a 4-valent vertex, then when I uncollapse it, I get that vertex, but I also get another vertex. There's another way of collapsing and another way of collapsing. Right? There's 3 ways of uncollapsing a 4-valent vertex to get it 2 3-valent vertices. Does that remind you of anything? So this is the IHX relation. So the co-boundary, this is basically the IHX. In this second row, everything has exactly 1 4-valent vertex. There's 3 ways of uncollapsing it to get 3 4-valent vertices. 2 3-valent vertices. Okay, so that's a nice picture. And then the lemma is the vertical columns have no homology except in the top dimension. So guess what? All we're left with is trivalent graphs with a bunch of trees in them, modulo IHX relations. So that's exactly the Lie graph complex. Yeah, I guess I'd stop there. So that proves the theorem that yeah, if I take the co-boundary, if I first do the vertical guys and do the horizontal guys. Yeah, if I first do the vertical guys and what's left is the stuff at the top, which is just exactly the Lie graph complex. Right. So we now have a topological interpretation also of the Lie graph complex. In particular, this proves Kontsevich's theorem that the Lie graph complex computes the cohomology of out of n. Okay. I was going to talk about the associative graph. So far I really want to talk about the commutative graph complex and the Lie graph complex. There's also an associative graph complex, and it can also be interpreted in terms of outer space. Outer space is covered by some spaces that are associated to ribbon graphs. And if you take one of these pieces, then its quotient computes the cohomology of puncturing mapping class groups. So you get a similar story for the associative graph complex. It's going to compute the cohomology of puncturing mapping class groups. You could also take there are other cyclic operads. There's the little disks operad. You usually think of that as little disks in the plane, but you can think of it as little disks in a sphere, in which case it becomes a cyclic operad. Or you can take the trained little disks operad, think of that on a sphere, it becomes a cyclic operad. And these are also interesting in low-dimensional topology. The framed little disk operad gives you the cohomology of Campbell-Wide groups, if you know what those are. But anyway, I put this up here with a blank space in case I had tons of time and didn't know what to say. But I think I don't have tons of time, so I'm not going to say anything wrong. Okay, so we have this nice interpretation of Kontsevich's graph complexes in terms of these spaces. So what can we do with this? Why is this useful? So we have a very explicit description of these complexes in terms of graphs. So for very low values of n, you can actually just compute the homology of these graph complexes by hand. Or hand usually means to the computer. But anybody that knows anything about graphs knows the number of graphs with a given Euler characteristic grows really, really fast. So this becomes infeasible. And when you do these computations, you get almost no non-trivial classes. So, you work and work and work really hard, you get one class, for instance, in H4 of the Lie graph complex of rank 4. And it doesn't tell you what's, it's hard to generalize. But a lot of interesting work has gone into trying to understand the homology of these graph complexes, in particular, the homology of the even commutative graph complex, GC2. So if you remember the exercise you were supposed to do in the break, I hope you all did. Well, you didn't, I did it actually, but the odd wheels give cycles in GC2. The even wheels are 0. It's not hard to prove. That was also an exercise. But the odd ones aren't obviously 0. And in fact, Thomas Wilbacher showed that they represent non-trivial homology classes in GC2. So what he did was really fascinating. He put a different grading on the graph complex. So the grading was by the number of edges of the graph minus twice the rank of its first homology. So we graded it by the number of vertices of the graph. But for this one, the number of edges, for instance, in this graph is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The rank of the homology is 5. So this has a grading 2. Zero. Nobody corrected me. You guys are asleep. N minus twice 5 equals
0.
Okay. In fact, all of the wheels occur in grading 0. So he showed that with this grading, the homology. So the boundary map also respects this grading. It takes things of grading k to things of graded k, k minus 1, excuse me. And so it's got a homology with this grading. And Wilbacher found a Lie algebra structure on H0 of the graph complex with this grading. And then he identified this homology group, H0, with something called GRT1. This is in 2015. This is the Grothendieck Euler Lie algebra. I forget what the 1 means. Maybe it's a unipotent version. I don't know. It's a Lie algebra. It's an infinite dimensional Lie algebra, and he identified H0 with this Lie algebra. So, and then, but it turns out that Francis Brown in 2012 had showed that this Lie algebra, which has deep connections to number theory and motivic homology, actually contains a free Lie algebra in generators in dimensions 3, 5, 7, etc. Odd, yeah. In odd dimensions starting at 3. And our classes, our simple cycles, these wheels turn out that Wilbacher could identify them with this wheel. So he proves that these wheels represent actually non-trivial cohomology classes by fairly complicated, it's easy to find a cycle. It's hard to prove the cycle is not a boundary. He proved this wasn't a boundary by doing some period integrals inspired by quantum field theory, showing that they didn't vanish. So anyway, he identified these wheels with these generators of this crazy Lie algebra. So what do you get? The cohomology of GC2 with R grading or with any grading actually contains this huge Lie algebra. So as an application, yeah, so first of all, this is great. It actually finds some non-trivial cohomology classes in the Lie algebra. And as I said at the very beginning, the cohomology of this GC2 is related to like knot invariance and homology d-square invariance and variance and cohomology of configuration spaces, etc. So cohomology is very interesting for all of these things. But here's another application which I really like, which is to mapping class groups of closed surfaces. So if you take a closed orientable surface of genus G, and I'm going to call mod sigma G the mapping class group. So that's isotopy classes of homeomorphisms of the surface. Then Herrer proved a long time ago in the 1980s that if you look at the isomology or cohomology, I remember I'm taking real coefficients here, so I don't care about homology, cohomology, and they're the same things to me sometimes. So Herrer proved that the homology doesn't change, the isomology doesn't change as the genus gets bigger, as long as the genus is big enough. So there's the stable homology was computed by Monson and Weiss in 2007 in a very famous paper. Monson got invited to give a plenary lecture in the International Congress of Mathematicians about it, so people were pretty interested. But nobody knows very much about the unstable cohomology of these mapping class groups. Previously, only finitely many unstable classes have been found. But these wheel classes that, yeah, right. Chan, Valetius, and Payne in 2018 showed that the cohomology of the mapping class group, kth cohomology, maps onto the 3G minus K minus fifth cohomology of GC2. So we have a ton of classes in the homology of GC2. So this gives a ton of classes in the cohomology of mapping class groups, and they're all unstable classes. So yeah. So this was big news too. What else? So that's a nice application of graph homology, even graph homology. Could go into more, yeah, okay. Now what about the odd Lie graph complex? Well, so the homology of the odd Lie graph complex is the homology of the quotient of the spine of outer space by out of Fn. The spine is contractible, out of Fn acts properly, so the cohomology of the odd graph complex in Rankin computes the homology of out of Fn. We saw that a little while ago. I don't know if you know if that's what you're saying, but that's what you're saying. And it turns out that Marita found cocycles in the Lie graph complex, the odd Lie graph complex, using Kontsevich's original ideas. Now I want to say a little bit about how did Kontsevich come up with graph complexes. I mean, he was thinking about algebras, right? And right. what he did for the commutative, he took, in this case, the free Lie algebra, and took a free Lie algebra on some generators. Yeah, how can I say this without? Right. And then from that, you can look at an algebra of derivations of the free Lie algebra. So if you have a derivation, it's something that obeys a Leibniz rule. And he looked at derivations that preserved a symplectic form, a symplectic element. And he used that, and so that's a particular Lie algebra that we call L infinity. And that's actually what he wanted to compute. He wanted to compute the cohomology of this infinite dimensional Lie algebra. This infinite dimensional Lie algebra has as a subalgebra the symplectic algebra ST infinity. Oops. And in order to compute the cohomology of the Lie algebra, we use a chain complex, which is the exterior algebra on L infinity. And since you have this action by a simple Lie algebra, the cohomology of, I'm saying all these words, it's okay if you just let it wash over you if you're not happy with these things. But I want to show you that there's some algebra involved. I know you guys all like algebra a lot. Right. The cohomology of this exterior algebra is the same. The chain complex, the Chevrolet-Arenberg complex, is quasi-isomorphic to the subcomplex of symplectic invariance. So the subcomplex of symplectic invariance, they're sitting in the tensor product of some V's with some pairings of the factors, which looks like a graph. So you identify the symplectic invariance with some graphs, and you get a graph complex. Okay, so that was a long story, but the idea is this graph complex somehow comes out of trying to understand the cohomology of the Lie algebra and passing to the subalgebra of the symplectic invariance. So what did Morita do? Well, he took the original Lie algebra that Kontsevich was looking at. That was L infinity, and abelianized it. So an abelian Lie algebra is a really simple graphic. It's zero. So if you can figure out, some the vector spaces here, the Lie algebra, which he did. Well, he understood some of it, but this map from L infinity to the abelianization A infinity induces a backwards map in cohomology, and he had some classes in A infinity, and they mapped to some classes in K. Okay. So all of this is using Kontsevich's original ideas to try to produce some classes mu K. So these alpha K's are never zero, and they map to some class of mu K. And Morita proved that the first one, mu1, isn't zero. And I forgot, I was going to write down the date, but time got away from me. It's around 2002, maybe. And then later, right. Well, cohomology of L infinity is the cohomology of the graph complex, which is the code. So Jim Conan and I reinterpret all of this stuff as just a bunch of graphs. So a cycle in this graph complex. And we proved that alpha 2 and alpha 3 are not zero from this point of view, and I didn't look up the date from that either. And But an open question for you all, if you, we wrote several papers about these classes, these cycles, which are called Morita cycles. We gave lots of ways of thinking about them, which allowed us to prove that the second and third one weren't zero. But we don't know whether they're all on zero or not. And this is really intriguing. Well, for many reasons. There's, let's see, did I say where they are? Yeah. UK is in H4K out of 2K plus 1. Now, this group out of 2K1 maps the GL 2K plus 1Z. So UK goes somewhere. And it's quite possible, given what we know, given the little we know about the homology of GL 2K plus 1, that at least half of the UK is mapped on to something non-trivial, because there is something non-trivial for them to map to. But why is this particularly interesting? The stable homology of GLN is known. It's got classes in dimensions 4K plus 1. That isn't 4K, but still there's 1 every 4 indices. And yeah, there might be some connection. Those are the Borel classes. Okay. So computing homology is hard, and finding homology classes is hard. So the next thing we do when we can't compute homology is look at Euler characteristics. So computing the Euler characteristic is a little bit easier. And computing the orbital Euler characteristic is even easier. Well, a little bit easier. So next thing I want to talk about, and Euler characteristics are going to give you information about cohomology, hopefully. So next thing I want to talk about, the final thing I want to talk about is what we know about Euler characteristics of some of these complexes. So let's look at GC2. So that's, we know chains are, it's got 1 generator for every admissible graph with Euler characteristic 1 minus n and no automorphisms. So it's 1 generator in dimension k. So computing the Euler characteristic, you can compute the Euler characteristic on the chain level, just as well as on the homology level. And so the computing the Euler characteristic becomes a graph counting problem. So what do you take? You take, right. The dimension of the generator is a number of vertices, V of G, and you're just counting graphs, and you're counting them with a sign, depending on the number of vertices they have. So, right, and we're only going to sum over admissible graphs, and we don't want any odd automorphisms of our graphs. So that's what you want to do if you want to compute the Euler characteristic. That's actually already still a pretty hard problem, even just counting graphs. But you can modify this by, instead of counting -1 to the V of G, you can weight this by the group of automorphisms of the graph. So instead of doing sum -1 to the V of G, you do sum -1 to the V of G divided by the group of automorphisms of G. And again, we're looking at G admissible with no automorphisms. So combinatorialists know how to count things. They know how to count graphs. They have lots of tricks for producing generating functions that count graphs, and for eliminating the graphs that you don't want to add, and for going from connected graphs to disconnected graphs and back and forth. So combinatorialists have a lot of tricks, but it turns out that the physicists also have some tricks. Their main trick, as far as I can tell, is if they want to compute 2m minus 1 double factorial, that's, they compute that as a Gaussian integral. I'm not going to get it right. E to the minus something or other. Okay, so I told this problem to some physicists at a physics conference, and yeah, sorry, I'm getting ahead of myself. This is true, that they have these tricks for counting graphs. But yeah, so anyway, you can use one of these physics tricks, especially this Gaussian integral, and get an answer. The answer is that the orbifold Euler characteristic of this is 0 if n is odd, and it's the nth Betti number divided by n times n plus 1 if n is even. Sorry, the Bernoulli number. After talking for 2 hours, yeah, the words don't come out right anymore. Okay, so that was actually done by Kontsevich. Well, the answer was put in Kontsevich's original paper. There's an exposition in a paper I wrote a couple of years ago, so that I actually understand the answer now. This is something, Kontsevich's papers are full of fantastic stuff, but it's all very cryptic, and it takes a long time to understand. So, yeah. The story about the odd graph complex setting, that was, and how it's related to the cohomology out of Fn, that was in Kontsevich's original paper. It was occupied 1.5 pages of proof. Jim Cohen and I wrote a 40-page paper explaining the details. So, yeah. Anyway, I'm getting anyway, so I've been talking basically about ancient history for a long time now, but I'd like to point out that about a couple of weeks ago, Michi Berinsky, who's a physicist, just computed the actual Euler characteristic of GC2. And he also figured out its asymptotic behavior as n goes to infinity. And I forgot, and yeah, you have to look at the paper to look at the exact expression. But he's done it. And, right. And the conclusion from these computations is that there's a lot more homology in the even graph complex than we've ever found. So in particular, this Freely algebra is only the tip of the iceberg. And I guess I wanted to mention how Berinsky got started on this. He first started, I told him about this problem about computing the Euler characteristic of out of Fn, which is, as we all know now, the Euler characteristic of the odd Lie graph complex in rank n. But thinking about it in terms of outer space and the action of out of Fn on outer space, or actually on the spine of outer space. And so in 1987, John Smiley and I calculated the orbital, the generating function for the orbital Euler characteristic of out of Fn. And like the commutative case, it's computed by counting graphs. So it's a sum over pairs consisting of a graph and a forest, minus 1 to the number of edges of the forest, divided by the order of the automorphism group of the graph modulo the forest. And we used combinatorial counting methods to produce a generating function, which was horrible. You could feed it into a computer. We did it for n up to 10 and got some answers for numbers out. Don Zagier did it, got numbers out for n up to 100. All of the numbers were negative. And they seem to be getting big pretty fast. And that's what we knew. But we couldn't prove, for instance, that they're always negative, and we didn't know how fast, whether they were always going to get bigger or how fast they were going to get bigger. So, right. So Michi Berbrinsky and I in 2023 calculated the orbital Euler characteristic of out of Fn using these, by inserting these techniques from quantum field theory. We proved that in fact it's always negative and it grows like n over e to the n, 1 over log n squared as n goes to infinity. So that's very fast. There's a lot of cohomology there. Interesting fact is that this, the homology of out of Fn is equal to the homology of out, is isometric to the homology of out of Fn plus 1. It exhibits the same homology stability phenomenon as say mapping class groups, but the stable homology is 0. That's a theorem of Galatius. Okay, so stably there isn't any homology at all. Unstably, there's tons and tons and tons of homology. We know, let me see, we only know one class. No, the Merida classes. We know 3 Merida classes and 1 other class. And oddly enough, the Merida classes are even dimensional classes, but the Euler characteristic is negative. So most of the homology is in negative dimensions. We know 1 negative class in H11 and out of F7, I think. Okay, so there's a lot of work to be done there. Where is all this stuff? Right, and maybe I'll say the last thing I'll say. I'm trying to catch a bus at 12:30. In a paper that just came out, we actually calculated the actual Euler characteristic of out of Fn, not the orbital Euler characteristic. And it's interesting, it's pretty close. This was and what its asymptotic behavior was. So this was the formula for the asymptotics of the orbital Euler characteristic, and it's off by e to the minus 1/4 from the actual asymptotics. Right. So this is also the Euler characteristic of out of Fn, the alternating sum of the Betty numbers. And or you can think of it as the Euler characteristic of delta n, which we remember is the Euler character is outer space mod. Oh yeah. Yeah. I forgot to tell you some, no, I was Rich has a new life, as of about 5-10 years ago. So delta n is, so outer space is the space of marked graphs. What does the out of Fn action do? It changes the marking. So in fact, the quotient is just CDN out of Fn is space of metric graphs. So another name for it is MGN of rank n. So as I said, this is acquired a new life. The tropical algebraic geometers came in and discovered the space, and they used to call it the moduli space of tropical curves. Tropical curves and sexy-living graphs. And actually, they don't like this one because it's not compact, and they actually looked at something, they compactify it, and what do they get? They get CDN star, not out of N. So they might call that space, so I call that delta N star, but they call it the moduli space of tropical curves, compactified. And last thing is the stuff at infinity turns out to be acyclic. So the homology of this is the same as the homology of that. Turns out. Anyway. And all of this is computed by the. Okay, I think I'm going to stop there.
Thank you very much. Questions?
Are you actively, like, do you have an idea where to look for all those classes that you can't find?
Not really. I have an intuition that these classes lie close to the VCD. So the one class that I told you that we have found, that's actually in the VCD of out of Fn, which is bizarre because in the cohomology, the mapping class group, or the cohomology of GR and Z, there is nothing in the VCD. So I kind of suspect that it's all near the VCD, but I don't really know. Yeah. But it's an interesting question. Well, I mean, it's interesting, yeah. Yeah, but I have no idea for any constructions. I'm still worrying about whether these Morita classes are non-trivial. They're very concrete. And it's, it's easy to see their cycles, even without going through Morita's. I mean, from the point of view of graphs, there's it's just a bunch of cubes associated with graphs glued together, and you can draw them, basically. But whether they're boundaries, I don't know. The proof that Vogtmann's proof that these wheel graphs are non-trivial in homology is quite difficult. It uses a lot of stuff. So yeah. Yeah.
So for the moduli space of curves,
Mm-hmm.
the points of the boundary that is interpreted to like stable curves.
Mm-hmm.
Is there some interpretation of the points of the boundary for graphs with them?
Well, I thought you were going to ask me whether the points in the boundary in the Delaney-Mumford compactification are correspond to points in outer space.
Okay, sure, yeah.
And they do, I'm looking at it. So I'm gonna answer the question, I know how to answer them. Oh, yeah, I can answer the question, but I want, so, yeah, you graph. Then, curves, sorry, and you take a bunch of curves and then a curve complex. A bunch of disjoint simple closed curves, and you pinch them all the points, you get what's called a stable curve. Yeah. Right, and dual to either the stable curve or the or the set of curves is a graph, which has one component, one point for each, one vertex for each component, and one edge for each pinch point for the curve that you just pinched. Right? So what you cover the boundary of Euler space, well, what's it, near infinity, the divisors and the dilemma for compactification by Euler spaces for surfaces for all these component surfaces, and they're all contractible, and the nerve of the cover is the curve complex, which is a bunch of graphs, and that's also related to outer space, which is a bunch of graphs. Okay. And that's the basis of Channing and Laetice's identification of the cohomology of a map from the cohomology of the moduli space of Riemann surfaces to graph homology. There's the graph. For outer space, yeah, so if you have a graph, how do you go to infinity? You collapse the loop. So if I collapse that loop, I get something like this, and I collapsed a genus one piece, so I put a one there. This is what the tropical geometers draw when they draw a tropical curve. So, yeah, if you collapse, yeah. So pinching a curve on the surface corresponds to pinching a loop in the graph or a subgraph, and pinching a subgraph makes you, if I pinched more, I pinched all of that, I would put a two. So yeah, there's a combinatorial picture like that of the boundary of outer space.
All right, if there are no further questions, let's thank the speaker again.